Okay, good morning. I'd like to talk to you today about D, nucleophilic substitution reaction. And there are a number of other things that are formed in this way, like polysaccharides and polynucleotides that are formed by phosphorus displacement. But we're going to leave that in the realm of the biochemist. And we'll start with one, polyalkylene sulfides. So these are materials that contain both CH2s and sulfurs in their backbone. The first one that we'll look at is starting with dichloroethane, which is not a common polymeric reagent, or ethylene dichloride, with a sulfide will produce an alkaline sulfide. The numbers of sulfur, and I won't balance this, the numbers of sulfur can vary in this particular compound. Uh, Generally speaking, these are mixtures of di, tri, and tetra, and even pentasulfide. So they're relatively small numbers of sulfur in the chains, not large numbers. And the average number of sulfurs is called a rank. The rank is always lower than the sulfur number that's used. So, for example, if you have a starting material that has 5 sulfurs in it, you're going to get less than 5 in the polymer. So some of it doesn't always all get used. And the rank is decreased by an excess of sulfur. So some of the sulfur compounds are favored. So some of these materials, if I have CH2SX, I guess I should have 2 CH2s. If X is equal to 1, it's a powder. If X is equal to 2, it's a solid plastic. And if S is equal to 3, it's rubber-like. I should point out that polysulfur is basically a rubbery material. So it's not surprising. Sulfur itself is inherently kind of rubbery. And again, I jumped the gun. This is just one with, this is what you do from dichloromethane. So this is just one CH2. Now, if you have the one with 2 CH2s, when X is 1, you also get a powder. If X is equal to 2, it's horn-like. So it's like a horn, like an animal horn, and it can be formed. If X is equal to 3, it's rubber-like. And if X is equal to 4, it's rubber-like, but crystallizes. On standing. So sulfur units are believed to be linear. There are some intermolecular interactions in these materials, and there may be some double bonds and there may be some rings, but as far as people can tell, it's kind of mostly a linear polymer. And this material has really good oil and solvent resistance, so it's often used for gaskets and sealants. Let me move my computer. I'm just worried that it's maybe not loud enough. How's that? Actually, hold on a second. Okay, in addition, let's talk about reactivity for a moment. You can make these from any, you can make these from different halogens. So one is that bromine's more reactive than chloride. That's not so surprising, but fluorine is unreactive. Fluorine really likes the electrons in the sulfur. Aromatic. Or vinyl halides are less reactive. So that's why most of them tend to be linear, unless they have strongly electron activating groups. And primary is the most reactive over secondary, over tertiary halides. These latter ones undergo dehydrohalogenation. Okay, and C is for cross-linking. You can cross-link these. You can use something like, too many, wrong place for the double bond there. I guess I want a Cl here, and there's no Cl in my notes, but there must be one. Let me add one. Okay. So you can cross-link it this way. That'll go to polymerization, and then you can do a vulcanization. Now remember, vulcanization is treatment with sulfur. So you already have sulfur present, and so this material can kind of self-vulcanize. And you can make nice rubbery gaskets from it. You can also use trichloropropane. So you have a trifunctional alkyl group as well. Okay, so the next number here, Although something's a little weird. I seem to go from 1 to 3, so I'll try to adjust this on the way. So 2. Polyphenylene oxides. So polyphenylene oxides, they're often successfully prepared by free radical coupling. We'll see that in a little bit. And often the meta isomer is done. So let's look at a couple examples. So we have like an aromatic alkoxide with a bromine group. Guess what? We're going to end up being liberating potassium bromide, but in the presence of a copper catalyst. We make the meta isomer of polyphenylene oxide. In this case, it is possible to, oh, and by the way, so this is in KOH as well. So you wind up with like the alkoxide. Molecular masses, 2,000 to 7,000 are possible. 17,000 is typical. A second way to produce this material and there are various ways of doing this, is with a like a diazo kind of compound. In this case, we'll draw it for the para isomer. Obviously, in KOH, we wind up with the O minus. This is a diazoide. Or diazo oxide. Similar kind of reaction, and you wind up with, obviously, the para-substituted material. Well, I think we're going to talk about a little bit more about this a little later, but you could guess what some of the properties are. So this looks like a bunch of phenyl rings together with an oxygen. The oxygen provides a slightly flexible link. The material is going to be thermally stable. Going to have some good high temperature properties. Probably not going to be terribly soluble. And it has a variety of higher temperature kinds of applications. These generally have lower molecular weights. Oh, and to balance this, we wind up with the nitrogen coming off. Okay, so 3 then, polyphenylene sulfides. You can make branched polyphenylene sulfides. You can start out, for example, with dichlorobenzene. Plus sulfur. Plus the disodium sulfide. And you wind up with a polymer. This polymer is not so different than the one that you saw before. It's a similar kind of reaction. This polymer, though, is complicated, but it's cross-linked with sulfur. And surprisingly, because of the aromatic ring, has an 85-degree TG and a 288-degree TM. That's pretty high when you think about it for sulfur-containing materials. But these tend to be branched, if not cross-linked. You can also make linear ones. For the linear ones, you can start out with a metal-containing para-substituted phenyl. And X here is a halide, can be chloride, bromide, which is the best, or iodide. And the metals tend to be lithium, sodium, potassium, can also be copper. And obviously what you're going to do is you're going to produce the salt, but the result of this reaction is and now once again I have to apologize, I guess I'm not quite awake yet, but the TM and TG for these are for the one below, not the one above, because the one above isn't going to have melting temperature because it's highly branched. So let me take this and move it below. I know that's not as easy for you to do. There. And just note that this TG and TM correspond to the linear polymer. Obviously, you can't have a crystalline material from a branched polymer. Well, if there are enough branches. So this material is highly crystalline. It's solvent resistant, low coefficient of friction. It can be sprayed on, and it's stable in air. This material, this polyphenylene sulfide, I know it looks a little, I don't know, weird, but it's very chemically inert. And this is the material that you mix with tetrafluoroethylene. And you polymerize that, and then what you wind up with is non-stick cookware. So many of the pans that you have that are non-stick, those are materials that are kind of blends of polyphenylene sulfide and polytetrafluoroethylene. I don't know what you guys think, but I never would have expected that a mixture like this is going to be useful for something like nonstick cookware. And apparently, when the polyphenylene sulfide decomposes, or the Teflon, it's not terribly harmful. Okay, so that was 3. So 4 is polysulfone. Polysulfones look a little strange, but they're actually quite useful, and they've got quite good properties. By the way, all of these polymers that I'm talking about in this section tend to be things that have a higher value and a higher cost. So again, and you notice a theme here for this kind of nucleophilic substitution. You have a lot of things that look like alkoxides and so forth. So here we have a monomer that you've seen before. Remember the name? But again, it's the dialkoxide, and it's reacted with a dichloride. In this case, the dichloride contains a sulfone. Here's your sulfone. And, okay, I wrote these kind of big, which is fine. Let's go down here. This doesn't always work so well to draw backwards, but let me do what I can. Actually, I'm going to try this to see if I can draw it backwards, but let's start with an oxygen here. Kind of weird to draw a phenyl ring backwards. Check my structure just to make sure I got it right. Double check the repeat unit, and I think that's okay. This material is called Udel, and it has a TG of, what do you expect? Probably something that's pretty high, 190 degrees C. Now, this material is tough. It has good impact resistance. It has good electrical properties, and it's used for things like power tools, circuit breakers. If you open up a circuit breaker box, the circuit breakers may be made from that, and also battery casing. So you got chemical inertness plus electrical resistance. Works pretty well. A related compound is this one. It's kind of more of a single one than a double one. And this material is diphenyl ether sulfone. And this material too has really good electrical properties. Interestingly, it's self-extinguishing in terms of a flame, and can be injection molded. So polysulfones are one of these two mostly, and the sulfone, just to repeat, part is this business here. So sulfur sometimes gets a bad rap, but it can be very useful in some of these compounds. Okay, that brings us to E. Should have been F, free radical coupling. Free radical coupling is just about what it says. You bring two radicals together. So the first one are aryline ethers. This was first made in 1916 by somebody named Hunter. So what you've got is, again, a derivative of bromobenzene. In this case, you got orthometa-para. Sorry, you got ortho-para substitution of the bromines. And then you got, again, it looks kind of like an alkoxide. So this, in a way, it seems formally similar to what we've seen before. By the way, you can also do these with phosphorus, and phosphorus has a greater reactivity than silver. And in particular, what I'm talking about is phosphorus as a replacement for what's going on there. Okay. Anyway, the reactions in our reaction section, but basically you form two radicals and the easiest leaving group appears to be this para substitution, and so you get a free radical that's kind of around, you know, basically you get free radicals here and here, and so you wind up with a para substituted generally, and but you can also get some other substitutions as well. Now I'm drawing these like it's a block copolymer, and I don't mean to imply that, but what I am saying is that you get various substitutions on these. So when these come off here, there's yx of some of these and some of the others. So you understand what I'm trying to say here, that these are not blocky, but you get some of the, I guess you would call it meta substitutions and some of the ortho substitutions. But it's my understanding that there's more of the ortho. Okay, so this material, in terms of reactivity, you can use phosphorus instead of oxygen for that group, but for the halogen, iodine reacts faster than bromine, which reacts faster than chlorine. Probably it has to do with how easy it is to leave with the electron, and so there are other substituents that work too. Another kind of compound that you can make from this, and so here's an example of other substituents, is this guy. So you've got the diphenyl substituted. Now, this requires some O2 or some kind of oxidizer with some copper halide. And this material is 2,6-dimethyl phenol. Nope, no parentheses. Okay, and the use of methyl group is okay. If you start making these chains longer, they tend to favor the dimer. And what's made at the end then is pretty obvious. Now, the methyl group is not a particularly good radical leaving group, so that here you get almost exclusively the para isomer. Well, you get exclusively the para isomer. And this is the material known as polyphenylene oxide. Since phenylene oxide is two words, I probably should put a parentheses around here. Okay, and I'll put quotes on it. Now the quotes just mean that this is not the only polyphenylene oxide. The most logical, simplest structured compound would just be without those two methyl groups on there. But then you'd get a mess, right? Because you could get ortho-para substitution. Remember, try and draw resonance structures. If you take one free radical off there, question is where does the radical go? It goes to the it goes to the ortho and the para substitutions. So in this case, they're blocked with methyl groups, and consequently, you wind up with a para. You wind up with a parapolymer. Okay. So this material has a Tg of 210 and a Tm of 338. 338, pretty darn high. And this material is known as parylene. So parylene, GE put this out as a blend of the polyphenylene oxide with polystyrene. Now there aren't too many blends out there because it's hard to get two polymers to mix together. But this parylene material has great dimensional stability. It has a very high thermal resistance. I mean, the crystals don't melt to 338 degrees, so it's a very high temperature polymer. It doesn't get rubbery for the non-crystalline segments until 210 degrees. That's a pretty high glass transition, and it has good electrical properties, good water resistance, has dimensional stability and good processing. So this is a material that can be used for a variety of high performance kinds of materials. So next one, aroline, alkaline. I hope you guys wanted a lot of chemistry today and the previous one. A lot of chemistry here, so you can't say this isn't a chemistry course. You might wonder why I talk so much when I do this. Probably because I miss the interaction with the class. And I understand that it's easier to go back and listen to what I'm saying, but I'm just used to talking, and I guess I like hearing myself talk, which is kind of odd. Anyway, so if you have diisopropyl benzene, you can use the dimer of T-butoxide, which looks kind of free radical like. So what do you got? You got two of these that are stuck together, so it's got to be an epoxide, like two oxygens together. So that's going to break apart, form two free radicals. So obviously you get a couple free radicals where those hydrogens are, and the material that you get out of this is this material. And so this is an aryline oxide. And so this is again a high temperature material. This material has a soluble fraction and it's crystalline, and it has a melting point of around 300 degrees C. So again, another high temperature material. Not quite as high as this guy, but you can see that it's similar. You got a couple more methyl groups and things in there, so they probably interfere a little bit with the crystallinity and make the crystals a little less likely to form. All right, now, here's a section that I added yesterday. On polyaniline. So, polyaniline. I'm going to tell you what I think this story is. But if you read the literature, it's pretty hard to figure out why this works. The reason I'm interested, the reason I point this out is that polyaniline is one of the few compounds that has real promise as a conducting polymer. It's stable. We've used this material, we've made this material in various ways, used it as sensors for ammonia and other things. It can be doped, de-doped, lots of interesting chemistry with it. And so, what I want to do though is take a little time and talk about initiation. So what you do in this case, you can use various kinds of oxidizers to initiate. And so let's look at one of these. Let's look at this material. What is that? It's potassium persulfate. Okay, so we've got potassium persulfate. So what happens if you put this in water? It's slow to decompose, but when it decomposes, it produces two potassium ions. That's not the part that's slow. And two sulfates that are radical anions. Okay, so what is potassium persulfate? It's just the dimer of this. Okay, so you got two of those put together, and there's an oxygen-oxygen bond, and it breaks. All right, so you've got that. And then the second part of the reaction is, and I'm just going to deal with the persulfate part, that again, with water. And this turns out to be a faster reaction. What you do is you can get all kinds of products, but one of them is, that you form, excuse me, that you form I get bisulfate, I guess, plus, so where'd the radical go? It went here. So now you've got this hydroxyl radical, and that's pretty reactive. So, this hydroxyl radical, and there could be other species involved too. As I said, the literature's not totally clear on that. So aniline, which by the way was like the first major organic compound produced. It was made because you could make it into a red dye as well as other things. But the famous German chemical company, which is maybe the largest in the world, I don't know if Dow DuPont's bigger now, but it's BASF, Badische Anilin und Soda Fabrik. So one of their main initial products was aniline, and this reacts with aniline, and it produces hydroxide ion plus the radical for the aniline, but it's got a plus charge and it's a radical. So basically, you kind of take an electron away from aniline. Okay? That's the important part of this step. Okay, so once you've done that, we also recognize that there's another resonance structure that's important. Oops, let me not do a ring there. And that other resonance structure is where the radical, and you draw one for meta too, but this is the most important one. Other one is here. So I've got 3 double bonds there. The plus charge still resides on the nitrogen, but I have 2 situations here. One where I have the radical on the NH2, and another one where I have the radical on the para position. Now, when I have a lot of persulfate around, and this is not like a catalyst, it's not like an initiator, you pretty much need at least one, since you get 2 of these, you pretty much need 1 persulfate for every 2 anilines that are going to react stoichiometrically. So now I've got this situation where I can have this kind of radical and this kind of radical together. Now, if I have 2 radicals and they're both, you're thinking about why not just react 2 of the radicals on the left-hand side with the radical on the nitrogen, because they both have positive charges, so the nitrogens don't react with each other. But it could be that if I have 2 of these together, that radical can react with the nitrogen, and that would yield a material. Let me draw it this way. And so here I'll just throw some double bonds in for this one. It's not very important, nor is it for here. Okay, so now I have basically formed the first dimer. Okay, and you lose 2 H pluses in the process. So now you continue to go, and let's react it with some more persulfate or the hydroxyl radical, And so basically what you wind up doing when you do that is you wind up taking away electrons. And so what you wind up doing, let me draw it again, just so we're all on the same page. When you take away that first electron, you end up with positive radical again. And you keep doing the same thing. And then you can have two of these, and eventually what you wind up with is, I think I have enough room to draw this, is oops, it's not going to let me finish this. I'm going to regret this. Yep, going to have to move it down here. Okay, that should work. And so then down here there's another one. And so you keep repeating that process with taking the electrons away, and you end up with polyaniline. And so there you are. Okay, and now I feel totally stupid because aniline has an I in it. That's embarrassing. So go back and fix this guy. Okay, moving right along. We go to F. F is aromatic. Electrophilic. Substitution. Now, one of these is polybenzyl. Now remember, benzyl refers to the CH2 being on the aromatic ring. So there's benzyl something. So this is generally a benzyl halide. Benzyl chloride, benzyl bromide, whatever you like, plus NH plus. Okay, so when you do that, you can make a carbonium ion which is kind of stabilized because of the aromatic ring, with the halide as a leaving group. That adds to an additional benzyl halide to produce it ran out of room again. Another group, and somewhere, probably ortho or para. So let's not specify where this comes out. Polybenzyl. So polybenzyl. You can get a bunch of rearrangements when you do this. It works as well for substituted aromatics, and you can do it with polymethoxy, polyisopropyl. You can do it with hydrogen on there. It seems to be consistent with a carbonium ion mechanism, and an oxidizing agent is helpful. So oxidizing. Again, this is going to be a material that's going to be somewhat intractable if there's multiple substitutions, and probably a fairly high glass transition probably won't be particularly crystalline. More important one is polyparaphenylene. So polyparaphenylene starts out from benzene with the help of an oxidizer. Oxidizers can be copper chloride, could be lead oxide, could be other things, and then a Lewis acid. Poster child for Lewis acids is, of course, aluminum chloride. Antimony chloride works fine. That's a 5 down there. Ferric chloride. And guess what? This one's real simple structure. Polyparaphenylene. What is the melting temperature for this? It's greater than 500 degrees C. I think that's the record for the course. Let's put a box around that because that's pretty cool. 500 degrees C, and you're not going to melt it. You're not going to form any other structures out of it because it decomposes. It decomposes before it melts. That's true of many of the kind of ladder polymers. Now, this would not be considered a ladder polymer. Why? Because it's only a semi-ladder. You kind of have ladder-like structure in the phenyl ring, but you have this flexible bond here. So you do have some rotation of that bond. Okay, and there's another way to make polysulfones via aromatic electrophilic substitutions. So this is a second way. So you look at that, looks nasty. It's like a chlorosulfone. Looks like it's pretty reactive. But you mix this with benzene, and it's kind of a Friedel-Crafts reaction. So you have a catalyst. Those are normally like FeCl3 or something like that. And so you do an aromatic electrophilic substitution, and you wind up with the polysulfone. Oops. Oh, I got that on there already. So the last one just comes off somewhere, not specifying what substitution it has. But again, this material, this polysulfone, has the properties of all the other polysulfones. It has good heat resistance, it's good for high temperature applications, and it has good electrical properties. Okay, so what I'm thinking is this has been almost an hour. It's been a lot of chemistry. Maybe it's time to take a break. When I get back on Monday, a week from next Monday, then we'll continue on with multiple bond additions. Till then, you guys have a good time, and if you have any questions, feel free to email me. And if we need to talk by Skype or something like that, we can do that, or I can answer your questions via email. And so with that, we'll just draw a little line here and say bye for now.